So good afternoon. Thank you for coming. I'm going to introduce our speaker today. Since we're doing a recording, this is the first time we're doing a successful recording, so it's going to be a good time. So let me introduce the speaker. Wendy Mendoza is an undergraduate physics major at the University of Texas Rio Grande Valley and a research assistant in the Time Domain Astronomy Group at the Center for Gravitational Wave Astronomy. Wendy is an active observer at the Cristina Torres Memorial Observatory in Brownsville, Texas, where she fulfills her research interests involving the observation of asteroids and their physical properties. Wendy, please take it away.
Hello everyone. So I'll be presenting the astral rotation of the light curve, and it will be my first research experiment that I did during the summer with you guys. So I'll be talking a little bit about what are asteroids, and asteroids are known to be small rocky bodies that orbit around the sun. They are also known as minor planets and also as planetoids. And asteroids are made of rock, metals, and other elements. Usually asteroids are located on the main orbit belt, which is between Jupiter and Mars. But it's not just only the main belt, there are also like the Trojan asteroids, which are the two asteroids share the orbit with Jupiter, and then the Apollo asteroids, which are spent, most of the time outside the Earth orbits, and then the Amor asteroids, which are asteroids that cross the orbit of Mars, but do not reach the Earth orbit. So the purpose of the experiment, I was able to plot the light curve of the asteroids. Asteroids are, they're due to shine the sun reflecting and of the light. So whenever the asteroid rotates, the sun of the light will catch that brightness, and it will help us to identify how much the asteroid is moving or rotating. So this is the asteroids that I observed. I actually observed 12, but I wasn't able to put the 12 because I'm waiting for someone who's willing to continue to do that observation of the other asteroids. So the asteroid that first I observed was a 22 Calliop. Sorry if I'm saying the wrong name. And with a spectral type of M, and the 34 Circa with a spectral type of C, and the 150 NOAA with spectral type of C as well, and the 243 EDA with spectral type of S, and the 289 Croatia with spectral type of X, with their brightness magnitude between 12 and 14. So the experimental procedure, I used the following: Gardusian, phototive, outer star path, astrometra, telescope control, and the observatory looking at the sky at the bottom, and as well as the neat 16 LX 200 telescope and the new Apogee Alta F 16M. Usually,
you use the Apogee actually.
Yes.
You didn't use the Santa Barbara.
Actually, Sebastian and I reinstalled the new Apogee with the guidance of Carla. Carla only told us what to do and how to do it, so it was a really nice experiment. And I actually like the Apogee F16M. This is some of the images that we took just for fun, which is the M60E with Nebula. The Nebula is right here, you guys can see it. And the Galaxy M101, and this was with Moises. I don't know if this is remember.
So these are actually F16, our camera.
Yes, with the
images.
Apogee F16. So, I really enjoyed the Apogee. So one of the experimental procedure was the cooling process. So the cooling process lasted about 5 minutes. We usually started with a 0 degrees Celsius, and then from there, throughout the observation, we lowered it down to -5 degrees Celsius. Then we did the alignment, which is our main star was the Arcturus star. This one. We always started with the Arcturus star before we began any observation, and then we started testing exposure, which lasted like 5 seconds or 20 seconds of exposure, and then getting our result was using Astrometrica and phototive. So the first asteroid that I observed was a 22 Calliop with exposure of 60 seconds, repeating the image of 20. As you can see, the max of our asteroid of the curve was the 0.029 Relative and the Julian time. The second asteroid was in July the 24th. It was the 243 Eta, and as you can see, the max was 0.04 right here, to the minimum of negative 0.045. And the third asteroid was the 34 Sitkin. It seems like it's in the same rate of brightness, so there's actually no difference between that. And then the 150 NOAA, was kind of odd, as you guys can see. I'm not sure, maybe it was like some technical difficulties, what's going on, but well, our max result was to be the 0.092. And then the last asteroid was 589 Croatia, which was around 11:20 p.m. That was the last day of my observatory that ended. The max was 0.058, and the minimum was negative 0.048. Sorry, but that's a really good curve, as you guys can see. And these are the asteroids that move. As you can see right here, you guys can identify that the arrow right here is because it moved by that direction, as well as the other ones.
But what happened with Sisi?
Oh,
No, I mean, the third one that you showed before, that one, why?
oh, this one. Usually this asteroid was around here, but since these two stars were in the middle, I just put the glass here. You guys can see that. How can I explain?
Oh, are you identifying these?
Yes.
Those are just markers to show, to
Yes.
point to the.
Yes.
Oh, well, I'm confused, sorry.
Oh, it's fine. Go ahead.
So, the first one, what is that red arrow showing?
That red arrow, it shows when the asteroid moved through that direction.
So, like, what is the first object, the one on the tail of the arrow?
That's the 22 Kelly.
And what is the other one on the tip of the arrow?
Okay, this is the 22 Calliope, and this is the star. The star. So the asteroid was located between here in the middle, and it moved towards this direction.
Okay.
Yes.
Oh, because the way I interpreted that, I thought there were two images that were superimposed, where you show where it was when you first started, and the second is when you finish. It's not that.
No, but
Okay,
it's
okay.
some kind of related to that because.
Oh, okay, because, thinking it was that, looking at the third one,
Yes.
you couldn't see how it's gonna go up and then down, which is what I thought it was happening, so, but it's not.
No.
It's just sort of showing the location or the trajectory
Yes.
of the.
Yes,
okay.
I do have videos, but I couldn't able to put them. It's on. You saw the videos, Richard, of how it moved. So, yeah, I'll show you whenever I have time. And these are the other ones. And these are my resources. That's pretty much it. So the purpose of this experiment, I didn't really follow any other type of experiment to see any changes. So anyone who's willing to work with me, I will be doing the same asteroids, but with different amount of exposures with longer period of time.
Sorry.
Yeah, okay. And I want to say special thanks to Dr. Diaz for allowing me to do this research, and Carla, who is not here, but she helped us a lot. Also Moises Castillo, and Richard, and Sebastian, which is not here, and Walton and Albert, who helped me a lot throughout this observation. So, thank you so much.
Any questions for our speaker?
Questions, complaints?
No complaints. This is nice.
Yes.
Very interesting.
One thing.
I have a question. Are you planning to observe more asteroids?
Yes, I do. I will be doing the same thing, but I'm also I hope if I'm lucky to find a new one that is not on the list, so I can at least name it my name or part of the group. That's my goal. That's my goal right now. So yes,
Honesty.
yes.
Now, the question I do have, if you know it, you observed 5 asteroids.
Yes.
I imagine that they do have a known period of rotation.
Mm-hmm.
Is it known, what is it more or less? How long they take to complete a rotation?
Usually, for me, when I observed, it lasted for 30 minutes.
Like in 30 minutes?
Yeah, like in 30 minutes. And it was not like a
Do,
big
do
of a
you,
change.
do you have data from those 5 already to show to compare?
And sorry, I don't mean to interrupt, but I don't think I don't think that the question was understood. Because I don't know if you're actually able to get the data for the actual rotation, right? So
Okay.
we needed more
Yes,
more
we
data.
need, we needed more data.
Okay.
So, like for instance, the asteroid that Lupe did, which was the previous summer, that had it was 5.8 hour rotation period. So you would need to
5.8
You
hours.
would need
Well,
to-
that's what I would have thought, and it may vary. Yeah, it probably would be good if you check what are the known, or at least the measure rotation periods so far, to have an idea of how long of an observation you have. Then there are many questions that I think of, and some of them might be stupid, but I still thinking of them. For example, how is related the period of rotation with the size of the asteroid? How are the periods of rotation related to the type of asteroids? Because I know there are asteroids made of different stuff,
Mm-hmm. Yes.
but I don't know much about it. It would be interesting to know that. So, to know, do they have any relationship to the stuff they're made of? I don't know. I have no idea.
Like their spectral type?
Yeah, for example. And I know that there are asteroids that are, they're not all the same, not only because they're different in sizes, they come in all sizes,
Mm-hmm.
but because the chemical composition.
Are you
is
saying
different.
the density might affect the period of rotation?
For example.
all of that. Actually, if you do color band photometry, if you take images of the same asteroid in different colors, based on the relative brightness in each of those colors, you can lump them into population types, like carboniferous asteroids, metallic asteroids.
Mm-hmm.
Old ones from the formation of the solar system or ones that would be captured or something like that. So,
I imagine that these ones that you're looking at, the ones that are within this, are more. Is that true?
Like the what?
How you call it, Amor? What do they call it, Amor? A-M-O-R.
like the Amur asteroid population, the Trojans, the near-Earth
Oh
asteroids.
no, the majority of these asteroids were like on the main orbit, the main belt.
Oh,
Yeah.
okay.
Yes.
Well, how do ones compare to the others? What are, one thing I remember we used to do as an exercise is getting precision on the orbits, which is sort of a different stuff. So, doing the astrometry, going to the database, which is in the Czech Republic, I think.
The one, the
The
near-Earth
near Earth
asteroid,
orbit, near Earth.
near-Earth object database, NEO, yeah, the NEO database.
And comparing with the existing data and improving the calculation of orbits. I don't know, I think it would be cool to explore all these different possibilities. These are just the questions that come to my mind,
Yeah.
but there might be more. I don't know if you guys think of.
Is there any
I have no clue. I mean,
All right, okay.
no, I don't know anything about asteroids. Let me be
Oh.
frank. I have no idea. Well, yeah, I know
I mean,
that.
because I can imagine the density, right?
Well,
There's
you can-
metals in it.
They affect the orbit insofar as where they are in the solar system. So like the ones that are farther outside the solar system are going to have more of the lighter gases that the sun couldn't capture, and they're also going to be more like icy. So depending on where they are in the solar system, they're going to have different chemical composition.
And that will affect how it rotates. Or
Sure, all of that.
It might. I would imagine that it should.
For sure,
And-
the moment of inertia is going to change.
And yeah, it's gonna change the moment of inertia. But also you might have, you know, the gaseous one, the more gaseous ones that are coming from farther outside, they might have more eccentric orbits and then eventually get closer. You know, I think it comes in all sorts. So it would be interesting. I remember when Juan was working on this, we tried to find references on asteroids. Like a book on asteroids. I don't know if there's a book on asteroids.
There's a couple. There's a couple.
It would be good to take a look at those books
Yeah. Okay.
and learning more.
Yeah, I can do that for my it's Corpus Christi presentation. So.
It's also useful to look at the rotations because depending on what they're made of, they have a maximum rotation before they destabilize. So that's also something that you can look at as well based on, you can group together their rotation rates and you might be able to deduce, well, these all seem to have an upper limit versus this which has a higher upper limit. Maybe these are denser than these or something like that.
Yeah.
Something for you to do.
Yeah, I think if, you know, probably reading some references might, you know, lead you to ask some questions about that you can try to explore. But yeah, this is cool stuff.
Is it still recording?
Huh?
Indeed. Watch what you say. Any other questions for Len?
I think you may have already mentioned it, but what's the website or database that you use to look for if I want to track an asteroid tonight?
Okay. Well, Grande, it's a really good one, but the Minor Planet and Common Planetary Service, I usually use that one to know what asteroids to look for and which ones are going to appear. But,
If I could add, the Minor Planet Center is an international collaboration. From what we were told in the astrophotometry class by Carlos Colasso, one of our friends from Argentina, he says that this is one of the largest, most funded and helped collaboration for specifically for near Earth objects, because those contain the potentially hazardous objects, which are objects that you'll see news articles come out and they say object skims Earth, and when they say that they're talking about distances, the closest one that I've seen was 13 times the distance from us to the moon. Yeah. So
13 or 13?
13.
13.
Yeah, I think it was 13. Or not that I got mistaken. Maybe it was 13. Yeah.
It's pretty close. How big was that one?
It was, I think, I don't remember, but it was one that was found from one day to the next, and it was because it's small in size, so it's like, you know, something smaller than 5 kilometers, like something.
Well, still, listen, even if it's 10 by 10, or 10, you know, they're more like potatoes, but if they're like 10 meters in one side,
Yeah.
it's enough to kill you if it hits you directly, right?
Yeah, I don't remember the exact numbers, but it was one that came really close, that was fast, and that one was 30. I remember that one.
Well, the most recent one was the one that
The one in Russia?
in Russia,
Right, yeah.
which is what, a few years ago.
Yeah, that's what.
That made contact.
I think they made an estimate, but I forgot how big was that one.
Right.
Do you, anybody remembers
I
that?
don't remember the size.
It was on the order of, I mean, it was less than a meter. It
Actually,
was-
the most recent one was in Africa. It was 3 months ago.
Oh, okay.
Yes, I presented that, if you guys remember, but it was in Africa.
Uh-huh.
It was small.
If you've ever been to the meteor crater in Arizona, I mean, it's about 1 kilometer in diameter from rim to rim, and they're inside the museum. They have an actual metallic asteroid that they said is basically an analog to what caused the crater, and the asteroid's only like this big.
I have a picture with it if you want.
So it's like it's just this metal. It's only about this big, but it caused 1 kilometer diameter because it's moving so fast. So
How big is the one that extinguished the dinosaur?
I don't know why I thought 7 miles, but I'm not sure. It was maybe smaller.
I don't remember.
That's some miles.
It's a couple miles. I mean, it hit the Yucatan Peninsula. And
Yeah, and that one is actually in the, I think in the Gulf of Mexico.
Yeah, they knew this because when they go to the bottom of the seafloor, there's a specific radioactive isotope that's only produced in asteroid impact. So they knew that.
Yeah, I
that was
think it's
asteroid.
iridium.
Iridium. Yeah,
Yeah.
there's an iridium compound.
Well, 10 to 15 kilometers.
And the 15 kilometers. Yeah, so that's about
10
that's
to
about
15
right.
kilometers.
Yeah. That's-
So actually, let's put it this way, this type of research can save humankind.
Yes, I'm saving
So,
you.
is there like a specific composition of asteroids that get closer to Earth orbit, or it doesn't really matter?
No, it doesn't really matter.
No,
The,
it
the only
doesn't.
thing is the ones that don't cause much damage are carboniferous because most of them break up in the atmosphere. But it's actually interesting. This is something motivation for you because you said you wanted to discover ones.
Yeah.
If you're searching in the plane of ecliptic, that's going to be where you're going to most likely find them. And also, most near-Earth asteroids that are theorized to exist are not discovered yet. So a majority of near-Earth asteroids are still undiscovered, meaning the hazardous ones are still undiscovered. So there's motivation for you to keep looking.
Every few weeks, I see articles about ones that are discovered that are immediately flagged as potentially hazardous.
Yeah.
Like they just discovered it and they're like, yeah, so this is kind of close.
Yeah.
But also remember, until you have several data points, you don't know exactly where the orbit is.
Exactly.
So the only way to calculate it is to have, to observe it over several nights. So maybe you don't discover it, but you can make a contribution to a better estimate of the orbit. And that's worthwhile, of course.
Oh, sorry. Go ahead.
If for example, if you have two telescopes observing from the 2 points on Earth, then we can make a very good estimation for it. And if the baseline is bigger, then the estimation is better. So, for example, if we have the telescope in Argentina and telescope here, and we can observe the object simultaneously from both, then we can make a very accurate
Yes, accurate.
estimation of the orbit.
I'm trying to do that in the future because I spoke with a professor talking to someone with the McDonald's Observatory. So maybe someone could also help me doing the observation.
We have contact information if you want
Really?
to talk to someone.
Yeah,
Yeah.
so-
And detection criteria, I don't know if this applies to asteroids, but if you want to discover one, at least for a planet, I'm sure it applies to asteroids as well, is you need to show a shift in position and then predict the third position and then observe it. And if it's in that position, then you've made the discovery.
Okay.
So you need to see something move, predict based on that, and then find it there. So that's what you'd have to do.
Yeah, because there's so many that have been observed. And there's still uncertainty on many of them.
There's some that like they before they claim discovery, they have to be vetted, and what they'll do is they have to make sure that in the database of discovered asteroids that they don't match, and sometimes there could be perturbations that cause them to change the previous
That's right.
orbit that it had. So that discovered may be a rediscovery. So it'll better to have
Well, thank you for the advices.
And thank you for your presentation.
You're welcome.